Okay, let's get started. Okay, so we're working on logs, and we're really working on everything that we do with logs is based on the meaning of what a log is. So what is the log base B of A verbally in a statement? So tell the person next to you, do you remember? What is the log base B of A? What's the meaning of that? Tell the person next to you. Go. So it's not about, I'm not asking you to kind of say an equation. I'm asking you to tell me what that is. What is that? Not a mathematical equation or expression. Log base B of A is what? What is it? See who remembers. Let's see. How about Chad? That's right. Headphones off. Log base B of A is what? If there's one thing you learn in today's class, it is this, and you never forget it. Let's see, who else? Is it Eitan? Yeah, Eitan. The exponent of B when the answer is A, or the exponent of B that gives A, exactly. So if there's one thing you learn on this day where you'd rather be not in class, is the exponent of B that results in or gives A. Look, you can just read it left to right. Logs are what? Logs are exponents. The exponent of B that gives A. You can just read it from left to right. Logs are exponents. So it's the exponent of B that gives A. And if log base B is the exponent of B that gives A, now we can, based on that meaning, we can write a statement. What statement can we write? What statement can we write? Right, so we'd have to name this something. So want to name it X. And then we could say B to the X, the exponent of B, look, the exponent of B that results in A. See? So this is the key right here. So now I want you to rewrite all, I've given you, there's a bunch of statements here. Just want you to rewrite all of those in a different mathematical way based on this meaning of log. All right, so you think about this meaning of log for each one. So you go to the first one. You say, oh, X is the exponent of 2 that gives 10. X is the exponent of 2 that gives 10. So I could say X equals what? Log base 2 of 10. X is the exponent of 2 that gives 10. Therefore, X is the log base 2 of 10. So you're practicing this meaning and rewriting every one of these in a different form. Go. Some will require a preliminary step. Some of them will require that you do something first before you can make the transfer. Okay? before you can make the switch. All right. Compare with the person next to you. See if you're doing it right. Troubleshoot. You got a question?
the whole thing is the exponent.
Right. Then you gotta have that base.
Yeah.
Okay, let's see how we did. So let's do this one. So this is getting now to the point where this is like if we had a problem, a real world situation, we might end up have an equation like this, and our goal is to figure out what a particular value of k is. All right, so this is now like kind of transitioning to what will it look like when we have to apply this thing in a problem. So what do we have to do before we can apply this meaning? We got to get this 5 to the 2k by itself. So only when we have the 5 to the 2k by itself can we apply this meaning of log. Okay, so let's do it in blue here. So we're going to do q over 3 equals 5 to the 2k. Now we're ready to go. So what statement can we say about exponents here? Yeah, question?
Why couldn't you distribute the 3 to the 5?
Because 5 is to the 2k.
So you can't make 15 to the 2k?
2 times 3 to the 4th. Is that the same as 6 to the 4th? That's what you're saying.
Okay.
Right? So 6 to the 4th is not the same as, that's much bigger than 2 times 3 to the 4th.
Okay.
Yeah. Doesn't work. Okay, so q over 3 equals 5 to the 2k. So can anyone interpret that like as this statement here? What would you say? Adam? No, I want you to say the statement. This statement. Times? So what is the exponent? 2k. And what exponent is it? 2k is? The exponent of 5? That gives q over 3. 2k is the exponent of 5 that gives q over 3. That's just literally, you're just saying that literally. 2k is the exponent of 5 that gives q over 3. Therefore, 2k is? Right. The exponent of 5, you can do it left to right. The exponent of 5 that gives q over 3. So in the past, so many of you have solved these like by taking the log of both sides or taking the ln of both sides. Well, this saves a step. This is less work. Using the meaning is less work. Because now we're ready to say what k is. What is k? Yep. It's 1/2 the log base 5 of q over 3. Questions on that one? Okay, so what about, let's do this one right here. So what do we need to do first there? Alexis, did you get this one? So you're dividing by -2 first? Uh-huh. Equals? Okay, and here's one where we can actually find this value of z without a calculator. Yeah, question?
Yeah, in the previous one.
Yeah.
Can we solve the 5 squared first and make it log to the base 25 q of 3?
Yes. 5 to the 2k is the same as 25 to the k. Yep, that will work too. Yep, so he's saying, is 5 to the 2k, that's the same as 25 to the k. So you did, what, the log, k is the log base 25 of q over 3.
Yeah, log to the base 25 q over 3 equals to k.
Equals k, not 2k, equals k.
Equals k.
Yeah, k equals a log base 25 of q over 3. That's true. Yep. On this one now, so actually if we look at this one, we can actually get what z is. So does anyone see how we can, without a calculator now? How can we solve for z? We have 3 to this thing equals 27. It's rigged. It's rigged. Yeah. Okay. So he's saying that 27 is an easy power of 3. Therefore? Yep. And z is? -6. So this particular one is rigged so that once you see that exponential equation, 3 cubed is 27. So -z over 2 must be 3. And we can actually solve that one. Questions? Okay, how about what's going on here? So when you see ln, what is that exactly the same as? Log base e. Okay? What is a log base e in general? In general, what's a log base e? Which exponent? What kind of exponent? No. Log base e is an exponent of e. That's what it is. It's an exponent of e. So when you see natural log, this whole thing right here, any natural log of anything is some exponent of e. That's what it is. Natural logs are exponents of e. In this case, it's the exponent of e that would result in e squared. This is the exponent of e, or the exponent of e that would give e squared. What's the exponent of e that would give e squared? 2, right? So we can say k, right there, k is the exponent of e that would give e squared. So that's 2. So ln of e squared is 2. What in general is this? So if you see this then, what are we talking about?
Base times.
Okay, but what is it? Does anyone catch? Oh, is that? It's an exponent of 10. If you don't see a number there, the number that's implied is 10. Therefore, it's an exponent of 10. We're talking about this whole thing is the exponent of 10 that gives 1,000. It looks like it might be an 8. It's supposed to be a 0. Okay? So when you see log with no number, that the number implied is 10. So what is it? It's an exponent of 10. So this is the exponent of 10 that gives 1,000. What is it? 3. What is ln of 7? It's a natural log, therefore it is an exponent of e. It's an exponent of e. Which exponent of e is it? The one that gives 7. Natural logs are exponents of e. So it's the exponent of e that gives 7. Any other questions on these? I didn't do them all, obviously. So any other questions? All right, so let's see how we can use this to help us solve problems. Can I erase? Go on. Too late. You're a second too late. Okay, here's a problem. Okay, use what we're learning. Use what we're learning. Fine. So we got this investment. T is a number of compounding periods. Okay, so we could say T is years. And if T were years here, then what do we have? What's the 41, 86, 58? Initial investment. What's the 1.025 telling us if T is in years? He wants the 1 year growth factor. Agree with that? And what does that 1 year growth factor tell us? And how much is it increasing per year? 25% per year. 2.5% per year, right? So this is just 2.5% per year. And so how many years? This is going to take a lot of years, okay? That's a low rate, and this is $4,000. How many years would it take to reach 1 million? So figure it out and use what we're learning. Use what we're doing on the previous slide. I'm going to take attendance. This is today, 2 weeks from today. Okay, here we go. So how about James back there? How'd this go? Did you get started? Tell me.
So it's 1 million equal to 4,186.58 times 1.025 power t.
And we're trying to find. Good. Yeah, so now it's just like with the ones we did before, right? So you're going to divide both sides by 4186. And what? I just want to write that value down. What is that value?
238.86.
Agree with that? Other people? Okay. So the days of taking the log of both sides are over. We got a much faster way now, right? Just boom, we got it. What is T? T is the exponent of 1.025 that gives 238.6, which we write as the exponent of 1.025 that gives Okay, so here's the question. How do we get that number? In your calculator, it has 2 logs built in. It has the common log base 10 is built in, and then natural log. And those are both on the left side, down towards the bottom, if you have a TI 83 or 84. But it doesn't have just a quick one button for the log base 1.025. So there's what's called the change of base formula. There's a formula where we can do this by changing the base to whatever we want. And so we're going to choose either log base 10 or log base e to do it. So this is change of base. it says that the log base b of a is the log. So we can choose a new base, call it capital B. Anything we want. Log base capital B of a over the log base capital B of the original base. So how do you know which goes where? So the thing we're taking the log of, the one that's up higher, goes up higher. The original base, down lower, goes down here, and that's the log of this, or what we're taking the log of here. All right, so we can choose, to use our calculator then, we want to use a built-in function. We're either going to use capital B equals 10 or E. All right, yeah.
Can't you just use the
Yeah, yeah, but not all calculators have that. So, but all calculators have the log and the E. So I want to teach this. Yeah, there is a way in menu to go through and do that directly, but you can't do it with one button. That's my point. And some calculators don't have that. All right, so what are we going to do here? Let's choose. We'll choose base 10 first. So what is this equal to? It's equal to the log base 10 of 238.86 divided by. Got to keep the same base. So when you change the base, it's got to be the same base in the numerator and the denominator. And so the original base becomes what you're taking the log of in the denominator. So what does it equal? A whole lot of years, right? How many years to get 1 million out of 4,100 at this very low interest rate, 2.5%? 200 what?
22.
Is there a decimal on that?
It's 221.71.
76.
So the answer 222 is in fact correct, because at 221 years, do we have the million yet? At 221. No, we need more time. So it's not until actually 222 years that we have the million. So that's why this problem says number of compounding periods, because this would actually be, if the compounding periods were monthly, if we were making 2.5% monthly, then this might be a little more realistic, right? Okay, so now I want you just to see that the change of base formula works. Go ahead and do now, let's choose base E. So ln of 238.86 over ln of 1.025. What do you get? You should have gotten the exact same thing. Okay? That's the point of the change of base. You get to pick what base you want to change it to. And it always equals the original log. Okay, so to use your calculator with the one button deal, you're going to choose one of these two bases because those are the two built-in bases. Any questions on this problem? Can we go on? Last chance. Okay, now we got some serious work to do. Putting lots of stuff together here now. This is bringing back stuff from before and bringing in the new stuff, okay? So let's see if we can do this.
Thank you. Yes.
I'm less interested in D and more interested in 1, 2, and 3. Okay? D is a good question, but I just, for time's sake, I want to make sure we get to 1, 2, and 3. Okay, go. Do everything up there.
So that's 0.2 times the original balance sheet. Well, that's the original. 300 plus 0.2 equals 300 times so you divide by 300.
So you're on the using the day factor.
Other way to send it, right?
Right?
Okay. Tyler, did you get the function?
Yeah, that's what
I think is that what you said? How do we do on the function? We good? Cool. All right. So how can you just represent B? So let's not get the number. But how would you represent the answer to B? How could you just represent the answer to B? They're saying f of 7. Agree? Don't forget this function notation is so important as a way of expressing output values. That's a number. F of 7 is a number. It's the output when the input is 7. So in this case, it's the size of the wound after 7 days. That's the size of the wound after 7 days in millimeters squared. All right, so we want 20% of its original size. Let's see, who's up? Wyatt. How will we get 20% of its original size?
So first I found 20%.
Okay. Okay. So he's saying that means 60 millimeters squared. 20% of the original. Okay.
And I knew that was output function, so I set it equal to 300 times 0.116. Divided both sides by 300.
Okay. Then what?
And so I set the natural log of 0.2
Yep.
equals negative 0.131.
All right, so look, we got an exponent of e that we need. What do we have to take care of exponents of e? Log base e. Natural log of e is an exponent of e. So negative 0.1316n is, what exponent is it? The exponent of e that gives 0.2. Practice this. That's the exponent of e that gives 0.2. Log base e, or natural log of 0.2. So it's going to be natural log of 2 divided by negative 0.1316. How many days is that? So that's right in your calculator, right? So we've got a natural log, just natural log 2. Divide by negative 0.1316. What is it? What? 0.2? Sorry. Thank you. Natural log of 0.2. Nice and loud so we can go on vacation. Is there a mistake here? 1.2 days? 12.23 days. That was painful. No, I didn't mean this was the last thing we were doing. Questions on that one? Okay, what's the continuous decay rate? Remember, this is the stuff that students have a really hard time with. So looking at that equation, what's the continuous decay rate? Negative 13.16. This is e to the k. The k is the continuous decay rate. Negative 13.16. Is that the percent that the wound shrinks every day? No. The continuous rate is like an APR. Okay? How do we get the actual percent change per day? Yeah, we got to find our b value, right? This is like a, b to the n. And this e to the k is b. Just try to keep your brain on, because this is like the lowest performance. These questions are the worst on the exams. Okay? B equals e to the k, and what's that? So b equals e to the negative 0.136, which is? Zero point. Okay, so that's the true decay factor. E to the k then is the true decay factor, which gives us the true percent change, the actual percent change. In this case, what, 12.3? Negative 12.3. So a continuous rate of negative 13.16 means a true decrease of negative 12.3%, not negative 13.16%. That's the true percent change per day. Okay, be safe, have fun. See you Wednesday. There will be written homework from next Wednesday.